Okay, we've got video and we're ready to go. All right, so in class on Friday last week, we learned about linear regression. So somebody tell me what we do in linear regression. So we wrote this MATLAB code. Why? What were we trying to solve for in this problem? Not everybody slept through class on Friday. All right. What did we do on Friday? Yes, Greg. Right, so we had some data that we'd collected in the wind tunnel. We had velocity data and we had some force data, and we were trying to fit one curve to all those 8 data points that we had. And so at the end of the day, we had 2 unknown values, which represented what quantities out of our curve. What were those unknown values we were trying to solve for? A0 and A1, and what do those represent? They're not just random variables, right? They have meaning. Say it louder. Yeah, so we have our slope and our y-intercept, because we're trying to find a curve, a straight line, which is defined by the slope and the y-intercept, and fit that to our data. So on Friday at the end of class, we finished our program, and when we run this program, we get a plot that has our data points on it in the blue asterisks, and then it has our best fit curve plotted on top of that. And so this represents the best straight line that can fit and represent our data. And from this, we can use that to kind of say, what's the relationship between our velocity data, which is what we plotted on the x-axis, and our force data, which we plot on the y-axis. And now where we kind of stopped at last time was, okay, we've got this. How do we evaluate how well that straight line fit the data? Because we can fit any type of curve to our data. We could fit a straight line. We could fit an exponential curve. We could fit some sort of trig function to our data. But we need some way to say which one is the best representation of our data, or which curve fits our data the best. And so how do we do that? We have to have some way of quantifying that. So I'm going to jump back over to the PowerPoint for a minute, and we'll talk about how we determine what the best fit is. And so when we're doing regression, we want to determine an objective, repeatable way to quantify which fit is the best fit to our data. And so for each point, we can calculate the error. And the way we calculate the error, we got that equation up there, but what the heck does that mean? So if I were to draw my x and y axes. So for this problem, I have velocity on my x-axis, I have force on my y-axis, and I have a bunch of different points, whatever they might look like. And then I fit my curve to my data. See if I can draw a straight line here. Not terrible. Kind of straight. I'm not one of those people that just draw a straight line without a ruler. So we'll pretend like this is the nice straight line. And now that I have a line fit to my data, whatever it is, straight or not, I can calculate this error. And so for each data point that I have, what does this error represent? So at each data point, it's represented by an x-coordinate, x sub I, and a y-coordinate, y sub I. So every data point has an x value and a y value. X is our velocity, y is our force. And so the way we calculate this error is we calculate the difference between the y-coordinate of our data point, and then if I were to draw a straight line down to my best fit curve, this point here has x and y coordinates as well. We could call that something like x fit sub I and y fit sub I. The x value is the same for both my xi and my x fit I. Those have the same x value. The difference is the y value, right? Those are 2 different y values. The one up here, the one down here. And then the difference between those is what I call my error. So this is my E sub I, the difference between those 2 values. And for every one of my data points, I can calculate what that error is. the closer that the data point is to the line, the smaller the error value it has, right? So if I were to calculate the error for this point here, it would be smaller than that one over there that I drew. Yes, sir?
So why do you only do that in vertical direction and not like perpendicular to the best fit?
You mean not like drawing a line this way?
Or that, or like doing perpendicular to the best fit line?
Oh, perpendicular to the best fit line? That's a good question. But what we're really trying, because the x values are the same, right? And so what we're really trying to do is just look at the y kind of error in that direction. We don't so much care about the x axis.
So would the error be the same if you did in the y?
If you did it in
if you change the x direction, kept the y the same?
It would not be the same error. And the reason kind of why we're focusing on the y variable rather than the x variable is because the x is kind of the thing we control in our experiment. We changed the velocity and we've got some sort of force. That's our variable that we're getting out that's not controlled, right? And so if we were to use this curve to say predict a new point, so say now I know this relationship between my velocity and my force, and I want to predict a force at a velocity I didn't measure. So I didn't measure force at a velocity of 75 meters per second. But I could move over here to wherever x on the x-axis 75 is, and I could predict some point off of my axis. I could predict some force value off my axis. I don't do that in the opposite sense. I wouldn't say, here's a force, tell me what the velocity is. So that's why we calculate the error relative to the y-axis. Make sense? All right. So for each data point, we can calculate that error. And we've got to have ways to be able to quantify how good this overall curve is. So you might think, all right, I'm going to sum up all these errors for every one of my data points and figure out the curve that has the smallest error of all of my data points. Well, there's a problem with that. So if we look at this figure over here on the right, we have two data points, 1 point here, 1 point here. If I put that straight line, the solid black curve through those two data points, that minimizes my error, right? I get an error of 0 because both of my two data points are on that line. So the error for both of them is 0. What happens if I have this dashed line here? I'm going to have some positive error there, maybe 2, for example. The error over here is going to be, say, -2. If I add those two up, I'm still going to get net 0 error, right? That's a problem. So those two curves, the solid curve and the dash curve, give me the exact same error if I just sum up all my errors. So that's not a criteria that I want to use. It seems like a logical choice, but it doesn't really give us the best fit curve. We can have multiple curves that fit our points with the same 0 error. So we say, okay, positive and negative values were a problem. Let's take the absolute value. So we'll minimize the sum of the absolute values of our errors. However, that can also not result in a best fit. So we can have multiple curves that kind of fit all of our different data points, still minimizing our error, but we don't get one unique curve. And we're always trying to find the one unique curve that's the best one. So there's a couple other criteria. We can minimize the maximum error, but that also causes problems. And so the one that is the best kind of error criteria is to minimize the sum of the squared errors. And some people will call this the least squares approach. You might have heard that. Some people will call linear regression kind of a least squares approach. So we figure out what all these errors are, we square them, and we sum them all up over all our data points, and it gives us one unique curve that will fit all of our data over and over and over again. So how do we quantify this error? Because we need now some sort of number that would help us quantify what this error is. So typically we calculate what's called the coefficient of determination, or R squared, and the correlation coefficient, which is just R. So you may have, created some nice data plots in Excel, slapped a line on there, and Excel gives you a magic R squared value, and you go, oh, look, R squared. But we don't really understand what that is, right? We just get this magic number, and we go, oh, look, Excel's telling me that that's important. Now we're going to kind of learn what does that mean. So R squared is how we quantify how well a curve fits to data, and it tells us actually what percentage improvement in the curve fit we get by using some best fit line rather than just the mean to quantify the data. So what do I mean by that? So if we go back to our curve here, let's see. I was hoping I had another color marker. Let's see if I can find it here. Oh, good thing the partition's down tonight. I'm crazy with all my marker colors today. So if I were to fit just an average curve or a mean curve to this data, it might look something like this. So this is my mean curve. Oops. So I take the average of my data points and I plot a straight line through that average. That would be what I call my mean curve. And I want to compare that to my best fit curve. The R-squared value helps me do that. If I calculate the errors, or the same E value, relative now to my mean curve and to my best fit curve, I can compare those two values. And I can say how much better is my red line, my best fit curve, than the mean curve, right? We can visually look at it and we can say this best fit curve clearly fits our data better than the mean curve, right? That's an ideal situation. And in that case, our R-squared value is going to be close to 1. It's going to be telling us that that fit is generally good. If the R-squared value is close to 0, it means that it's basically a wash. It means that we could have fit the mean curve to it, or we could have fit some best fit curve to it. It doesn't matter. There's really no trend in the data. Usually that ends up having something like, if we were to have some sort of totally random relationship between our two variables, there's absolutely no trend in that data, then I would be able to fit a best fit curve to it. It would look like that. My mean curve would probably also look just like that, right? No big difference between the mean and the best fit curve. So that usually means that we have an R-squared value that's going to be 0 because there's no trend to the data and there's no curve that's going to fit to that data and actually mean anything or tell us anything about the data. So that's what R-squared actually means. How do we go about calculating our R-squared value, and what does that actually indicate? So R-squared values can be kind of deceiving. We saw examples of an R-squared value that was close to 1, and then some R-squared value that was close to 0. But we can also have R-squared values that seem relatively good. Like, for example, this R-squared, all 4 of these plots have R-squared values of 0.67, which would be considered okay. But you can see visually that all the curves don't necessarily represent the data. Sometimes they're thrown off by just the shape of the curve. So up here in the top right, we've got this kind of curvature to our data, but we fit a straight line to it. That's not a good representation of the data. And then down here on these bottom 2 plots, we've got some outliers in our data. We've got one point that's kind of throwing off all the rest, and it's showing that it's not a good fit to all the data points that we have. So we always, always, always have to plot our data and our best fit curve on top of each other, use our R-squared value, but with caution. So kind of evaluate what is our R-squared value? Is it a good R-squared value? And then visually, how well does that curve fit the data that we have when we plot it? So we don't always trust the R-squared value. So when we calculate the R-squared value, we do three steps. We use this error value, this E value that we talked about, the difference between the Y coordinates between our data point and our fit. We also use the difference between our Y value and our mean line. So that's the error or the E value away from our mean line. That's what that quantity is. And then we relate those two things together with this formula where we take the mean value minus the best fit value over the mean value, and we get this relationship between the two parts of the data. And whenever we do that, now we get that percentage of how well does the best fit curve fit kind of relative to that mean curve. So let's jump back to MATLAB and calculate that for the bungee jumper problem. Let's see. So if we jump back over to MATLAB, what we did at the very end of class last time was we plotted. So the only thing we have left to do is actually calculate our r-squared value. And just like I showed you in the PowerPoint, I like to do that in kind of a three-step process. So the first thing I like to do is I like to calculate my SR value, which is the sum of the E squared, or the sum of the difference between the Y values and the Y fit values. So I take my data and I say SR is equal to what? What quantities do I want to subtract here? So let's write it up on the board. So I've got SR is equal to the sum of yi minus y fit. If we go over to our MATLAB code, what variables do we have in our MATLAB code that we would want to use in this formula? What represents our y data points? The force, right? So our y data points are force data, or our force variable. What's our y fit in this problem? The force fit. So we used our curve down here. We used our best fit curve, our A0, A0 that we solved with the backslash operator, and we said we now have force fit values, or y fit values. So if I go back down to my SR calculation, what do I want to do? I want to take the difference between force and force fit, and then I want to sum them together. So what MATLAB code do I want to write to do that? Do I need to write a for loop to sum them together? Do I need to use something else in MATLAB to sum them together? Something else? The sum function, right? We have a sum function in MATLAB, so I can take advantage of that. Sum will take the sum of a bunch of values in a vector. So both force and force fit are vectors.
You want to get like just one number?
I want to get one number, so SR is just one number. So I'm going to take the sum of force minus force fit, and that's going to give me my SR value. Now we jump back over and we look at ST. So ST is equal to the sum of yi minus y mean. So yi is again my force data. Where is the y mean going to come from? Say that again? The mean of the force data, right? That's what we said the y value was, so that's going to be the mean of our force data. So when we write our ST equation, we want to use the sum again. So we want to sum those all up. Sum of force minus the mean of the force data. So we can use our mean function and take the mean of our data that's in our force vector. Then we just need to apply the formula there. So we say r squared is equal to st minus sr over st. So r2 is usually what I call it.
Don't we need a square in ST?
Do we need a square in st? Oh, you're right. You're right. Oh, and I'm missing a square here. We got to square both of them. Sorry. I will fix that in the PowerPoint. So we need to square before we sum.
Can you do it like in the next step, which is the r square?
You want to square it before you sum it, though. So we got to make sure that our squares are inside of our parentheses. Now, do I need dots in here? Yes or no?
No.
Dreaded dots. They're always coming back to haunt us, right?
Yeah. Because it's before the sum.
It's before the sum.
Which means we have a vector.
Force and force fit are both vectors. So we're going to have vector minus vector gives us a vector. Raise it to the second power. So yes, we need a dot there. And then on the second line, we also need a dot because we have a vector. This mean of a force is going to give us a scalar, right? But a vector minus a scalar is going to give us a vector. So we still have a vector that we want to square. We're going to square each of those values independently. So we put the dot. So now we need to do our formula. So we need to take ST minus SR and divide by our ST. Any questions about that? All right, let's run this real quick and see what we get for our R squared value. So we get our plot again. And then if we look at our R2 value, we should have something, it's roughly 0.88. So what does that tell us? Is that a good R squared value or a bad R squared value? It's not bad, right? It's not terrible. It means roughly that the best fit curve is 88% better than our mean curve. So it's pretty good. B plus, right? So not too bad. Honestly, with a lot of real data that you're going to collect, real experimental data, you're probably not going to get an R squared value much higher than 0.88. It's very near to impossible to get a really, really good R squared value just because we have error in our data, we have variability in our data, and so we don't really expect R squared values to be close to 1. All right, any questions about that? Okay, so now what we're going to do is work on an in-class exercise. So for this in-class exercise, you're going to fit 3 other best fit curves to your data. So I've given you the form of the 3 best fit curves, and so what I want you guys to do is kind of walk through how you would change the curve, what you would have to do to your code. So there's not a whole lot of code that you have to write to figure out what it is you have to change about your code to get it to work for other types of curves.